Good afternoon. Welcome to Krishna's class. Today we prove the main theorem that a given Hilbert space is isomorphic to L2A for some index set. Okay, so that's the theorem. So we shall first look at what we mean by isomorphism. Two Hilbert spaces H1 and H2 C or R are isomorphic if there exists a one-to-one onto linear map lambda from H2 which preserves the inner product. That is 1 lambda from H2 is linear bijection. Bijection means one-to-one and onto. 2 lambda of this is what you mean by inner product is preserved. Okay, I put sub 2 to designate that this stands for the inner product in H2 and this is the inner product in H1. H2. Okay. So H over C is a Hilbert space with inner product designated by UB, where U and V belong to H. Inner product of U with V designated by symbol. Let A be an arbitrary set. Then L2A is designated as set of all complex valued functions with the domain A such that summation over alpha belonging to A mod phi alpha square is less than infinity. Now this sum, see, we are not putting a restriction that A is finite or countable, and it could be even uncountable set. However, we know that if this sum is finite, then it is necessarily phi alpha is not equal to 0 only over a countable, only for countable values of I. Okay. Therefore, this sum is essentially a countable sum or finite sum. Want to distinguish whether A is countable or not. So you don't need the restriction that A is countable. Nevertheless, this particular sum that in fact designates the norm of phi is, or norm of phi square is is at most a countable sum. So that's the something that we require. Now what we want to prove is the following. So let me keep that there. L2A is a Hilbert space with inner product. This is the inner product that's given. Now we will start working on this. We have said what is the Hilbert space isomorphism, and now we can prove that any given Hilbert space is isomorphic to a specific Hilbert space L2A or some. That's what we want to. So this is what we have already, U alpha for alpha belonging to A, maximal orthonormal set in a Hilbert space H, and X hat alpha is equal to then the mapping is a Hilbert space isomorphism of H into this. We have essentially we have shown some equivalence in the last theorem. Okay, so what we are asserting is this, or what we have proved is this: if U alpha is a maximal orthonormal set in a Hilbert space, then if you write down the corresponding L to A, okay, then L2A is a Hilbert space. Okay, and uh, the map from X to X hat is a Hilbert space isomorphism of X onto L. Remember this isomorphism is valid only if it is a maximal orthonormal. That's what we have proved. Because the identification that we have made is the identification that we have made is the following. If U belongs to H and U equal to alpha belongs to this is the identity. Then you are identifying which is equal to, by our notation, this is X hat alpha. You are okay, using this notation. Then it is equal to is an isomorphism. So the point is this, I mean, as we have in the finite dimensional vector spaces, suppose you have an n-dimensional vector space over a field F, then you have a natural isomorphism of the vector space to a copy of Fn. Okay, it is the analogous theorem that you have here, right? So you recall if over a field F, then X is isomorphic to a copy of, and this is not unique. This isomorphism is not unique. It depends on the basis that you choose. On the choice of the order list. But what's clear is that instead of looking at the vector space and looking at the properties of that, you can corresponding you have a copy of that. So by understanding what is happening on Fn, you can understand what is going on in the vector space. Now you have this result for the finite dimensional space. Okay, this is n-dimensional. The result that we have stated here is essentially the analog of that. Okay, instead of Fn, what you have is L2, right? So if H is a Hilbert space, then it is isomorphic to this is the result that we have proved already, right? Now we have also seen that over here the art of getting the isomorphism is by choosing an ordered basis for x, which exists. Okay, here the corresponding art is choosing a maximal orthonormal set in the Hilbert space. Okay, once you do that, you have the isomorphism connecting H to H hat. So x belongs to for x belonging to H, you have x hat belonging to L2. So you have this connection. That is, x is connected to x hat. So there that defines the isomorphism between H and L2A. And you see that this is dependent on the maximal orthonormal set that you choose. So if you have, because it's not unique, choice of a maximal orthonormal set is not unique in a Hilbert space. There could be several such choices. Okay, and therefore there are several isomorphisms that you can define from H to L2A. But what is important is that there exists an isomorphism. Okay. Now, one of the immediate inferences that you can make are for two index sets A and B, and B, L2A and are isomorphic if and only if A and have the same cardinal number. Now that's easy to prove because you take L2A as a you have an H which is isomorphic to L2A, an H which is isomorphic to L2B. Okay, then you see that there is an isomorphism from H to L2A, H to L2B, and correspondingly you will see that between A and B there is an isomorphism. That means you have both these sets have the same cardinal number. Now, what we want to prove eventually is, so we have seen that if X is a finite dimensional vector space over F of dimension n, then then X is isomorphic to Fn. Okay? Recall this. X is isomorphic to a copy. We call the art of doing this. What was that? Choose a ordered basis for X and then connect. Right? Choose an ordered basis for this. I mean the art is this X. Then U belonging to X can be identified with the ordered n tuple this is the isomorphism that you have. So quantity is then phi is an isomorphism. Here we are doing the same thing. Okay, so instead of X, so compare this. That is H is a Hilbert space. X is a Hilbert space. Over C, then what we assert is that index set and orthonormal A is a maximal or what you call complete in H, then the map, what is it? U belonging to H alpha is an isomorphism. So corresponding to every H over C, you have an isomorphism from H to L to A for some A. Okay? That means you have a U alpha belonging to, essentially it means you have U alpha belonging to A is a maximal, there exists such a maximal orthonormal set. So in every H there exists a maximal or complete. So that is the only thing that we have. Okay. Therefore, we complete the proof of this result by showing that in every Hilbert space over C, there exists a maximal. Okay. So that will be our task. So we need for this some, because this is only true about a non-trivial Hilbert space. Okay, so let non-trivial Hilbert space. That's the basic assumption that. Okay. Then we assert that so that you get the correspondence between you getting associated with L2. This is an isomorphism. Okay, so once you have a maximal orthonormal sequence, do you know that this relation is a Hilbert space isomorphism? Okay, therefore the question reduces to, so once is an isomorphism. It is obviously not unique because it depends on the choice of the complete well. So what do we have to prove? So the problem reduces to proving that the maximal just changing it for consistency, even otherwise it is right. Okay? Every maximal orthonormal sequence is also called a complete orthonormal sequence. Yeah, right. Now to prove this, we require require some basic results partially ordered sets and totally ordered sets. Shall just give the definition and then come back to the proof of the theorem, or we will do it next time because we will define what's a partially ordered set, what's a totally ordered set, and then we recall the Hausdorff maximality theorem, and then once that is done, all the ingredients are there, the problem, the theorem is proved. Okay, it's a very short lecture that I have done because if I do the other part also, lengthy, so I want to avoid that. I stop at a convenience. Okay, thank you very much.